Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. I have Robbie Elbertse. He's a researcher at the University of Delft, or Delft University in Netherlands. He's developed a sensor that has only 11 atoms in its size, which is amazing. So we're going to talk about that, how he built it, how he conceived of it, and what it can be used for. So, Robbie, thanks for coming.
Yes, it's my pleasure.
Yeah, so what was this your concept, or is this someone else's concept that you're working to advance, or how did this come about?
So it's not my concept. So the paper that I worked on, which got published, it has me and someone else, David Coffey, as the main authors. And it was David's idea. He was doing a postdoc in our group, and I'm currently doing a PhD in our group. So he had a little bit more already experience in this field of research. And he actually came about the idea because he wanted to use some kind of sensor to measure something, but that sensor didn't exist yet, so it had to be conceived.
What does this sensor measure?
So what this sensor measures is so-called spin waves. And a spin wave you can kind of see as a magnetic wave that moves across atoms. So generally, when we think about waves, you can, for example, think of a stone falling into water, and it creates these ripples that go from the stone. Those are waves on the water, but there's also, for example, electromagnetic waves, light. But if you only take the magnetic parts, then you get magnetic waves.
So, I'm familiar with electromagnetism, but what are magnetic waves? Where do they come from? How do they propagate? Tell me something about them.
Right. So these atoms, they're, in my case, iron atoms, and they're iron atoms on copper nitride. And these atoms have a so-called spin. It's because they have uncoupled electrons that orbit around the nucleus. And these electrons provide a magnetic moment. And so this magnetic moment is what gives the iron its magnetic properties. And so each iron atom can have its own magnetic moment. And let's imagine we have a chain of, let's say 5 iron atoms in a row. Depending on how you orient them, these atoms or these magnetic moments can all point in the same direction. Let's say they all point up for north. So if we have them in a chain, then these atoms are so-called ferromagnetically coupled because they all point in the same direction. A wave would then be kind of like a wave in a football stadium, where the first atom, instead of pointing up, it starts pointing, down for a second, and then it comes back up. And then a short while later, the second one goes down for a bit and then goes back up. And then the third one goes down for a bit and back up. So it's kind of like a wave of these atoms pointing either up or down, and it moves across this chain.
So does this happen in only magnetic materials? Does it happen in disordered magnetic materials? When does this happen, and what's the consequence of it? How does it? What physical effects does it have?
So what you need is atoms that have such a spin, such a magnetic moment. So not all atoms have this, but iron is a good example where it does happen, specifically in our case. But so I described the situation of a chain, which is obviously very ordered. But if you just throw a bunch of iron atoms in a clump together, even there, the atoms will have a magnetic moment pointing in a certain direction. It will not be as neat where all of them point in the same direction. They can point in kind of like various random directions, or by coincidence, point in the same direction. Still, in these situations, there can be a magnetic wave, but they're super hard to understand because, for one, if it's already a disordered bunch of atoms, it's hard to understand that. And then add on top of that they start waving in different directions. and they can have multiple waves all happening at the same time. So while it is possible to have this in many different scenarios and situations, we try to find very simple situations so that we can understand them from their basic principles.
Well, okay, so you wanted to develop a sensor to determine what the magnitude or the existence of magnetic waves in various materials?
Yeah, so we do know that when we have this chain of iron atoms that there are magnetic waves, because we have been able to see how they reflect within such a chain. But what we didn't really know is how far do they travel. So, for example, this chain of 5 atoms, if I start at the first atom and then I initiate a magnetic wave, will it reach atom number 3? Will it reach atom number 5? What if I make the chain 100 atoms long? Will it reach the end of the chain? So we had some theoretical guess about that. But obviously, it's good to verify whether your theory actually holds true. And that's why we made the sensor. So the sensor is able to detect whether such a magnetic wave reached the end of the chain. So we didn't really measure in the middle of the chain, but still, if we can verify whether it reached the end of the chain according to a certain probability that corresponds very well with our theory, then we can say, okay, it appears that our theory correctly describes or seems to describe whatever we expect is going to happen there. And we found exactly that. So we used the sensor on this chain of either 3, 5, or 9 atoms. And we found that the expected chance of the spin wave reaching the end of the chain, based on our calculations, correspond very well with what we actually measure. So that's really cool.
Well, so what happens? I mean, what kind of materials do magnetic waves propagate in? Do they propagate in all materials, just not very far? I mean, if I look at various materials, do these magnetic waves constitute anything important about their material properties, or is it only certain materials?
Yeah, so you need the material to have such a spin, so these uncoupled electrons. Iron is a case. A lot of the so-called 3D materials, or such as iron, cobalt, nickel, they all have uncoupled electrons. And so with them, you can have these magnetic properties, and so you can have these magnetic waves. Let's say hydrogen, what also has an uncoupled, but helium, for example, helium does not have any uncoupled electrons, and so with helium you wouldn't be able to do this. So yeah, in general, most materials would allow for it. The nice thing about iron is that it has 4 uncoupled electrons, so it has a large magnetic moment of 2, because each electron adds half a magnetic moment. And also it is very nice because it's very abundant, so you can easily do experiments with it.
So if an element's electrically conductive, does that mean it's going to be magnetically conductive? I don't know if that's the right term.
I would say that is the right term, but not necessarily. So the fact that something is electrically conductive has to do with the band structure of the material. So that means how much energy does it cost for an electron to be excited to a so-called conduction band. And all metals have this conduction band very close to the so-called Fermi energy, so close to the rest, like the basis state, the ground state as we call it. But that does not necessarily mean that it has magnetic properties. Let's see, is there... So, for example, lithium is... lithium can have an uncoupled electron. Let me think for a second, which...
what about copper? Copper is very conductive. Magnetically, What's it like?
Yeah, so bulk copper does not have any magnetic properties. But if you look at single copper atoms, then the story is different. Because single copper atoms, I believe, have one single uncoupled electron. And so if you have a chain of copper atoms, you will actually still be able to induce these magnetic waves in it.
Okay, and then now to the sensor. So how does your sensor work? And I guess it's a huge deal. The sensor's so tiny, it's amazing.
Yeah. So the sensor, we say it consists of 11 atoms, which are 8 in the middle and then 3 on the side. And so these 8 in the middle it's a so-called bistable bit. So what happens is these iron atoms have a coupling strength with their neighbor. So these 8 atoms in the middle, they have a anti-ferromagnetic coupling, which means that if atom number 1 points up, then atom number 2 wants to point down, then 3 wants to go up, and then 4 wants to go down. So up, down, up, down, up, down. And that is one state that has the lowest energy, but there's a different state that also has the lowest energy, which is down, up, down, up, down, up, down, up, down, up. And so both these states, let's call them state A and state B, have the least amount of energy, and that means that they're stable. So if you start your chain of 8 in state A, it can easily stay in state A because it's stable there anyway. But if you're able to bring it to state B, it will just stay in state B. So what we then did is we have this bistable bit of 8 atoms, and on both sides, so the left and the right of it, for example, we add a smaller chain. On the right, we have a small chain of 3 that we use as a reset lead. And on the left, we have our input lead, which is the lead in which we, so this chain in which we make these spin waves. And since it's very weakly coupled to its neighbors, it can still feel the neighbors, but if both neighbors show a similar kind of energy towards the guy in the middle is happy to stay in either A or B, whatever it was. Now, the trick is that we bring it into state A, because then if we make an excitation in this, so a magnetic wave, spin wave, in our input lead, it's actually going to change a little bit the energy landscape to make state B more favorable. So then it will go from state A to state B. But that only happens if the spin wave was able to reach the end of the chain. If the spin wave was not able to reach the end of the chain, it cannot influence this bistable bit in the middle, and so it will remain in state A like it initially was. So how we do our experiment is we bring our bistable bit in state A, we try to induce a spin wave or a magnetic wave, and we go back to our guy of 8 and ask it, hey, are you in state A or in state B? And if it's in state A, then it's a suggestion that the spin wave didn't reach the end of the chain. And if it's in B, then it probably reached the end of the chain. And so we repeat this experiment hundreds of times to get statistics. For example, 60% of the time it reaches the end of the chain, or 80% of the time. And with that, we basically have some responsiveness of this bistable bit on our input parameters. And so we change our input parameters. We make more excitations, more spin waves, or we start the spin waves in a longer chain, or we start them further away. And so like that, we're able to both understand how our sensor works, but also how our input lead, so our spin chain works.
So what's the lower end threshold of, what constitutes a wave? If spin propagates through 3 atoms, is that a wave? Does it need to be 8? And, how sensitive is this instrument? Yeah,
so, on the one hand, that's kind of a question, when is something a wave and when is it just someone going... So, for example, in a stadium, if the whole stadium moves their arms up, it's obviously a wave. If it's just one person doing it and no one around it's doing it, is it a wave? Is it the start of a wave? Is it just a guy flaying his arms? We will, in either way, call all of them a wave because it's conceptually easier to just expand that from, let's say, 2 to infinite amount of atoms. But what we found is that these waves, they only last for like 10 picoseconds, which is very short. And since they have a velocity of about 50 meters per second, that means that we're only able to reach about 5 atoms long before the chain kind of decays, or before the spin wave decays. So when we made a chain of 9, we only saw that the first couple of atoms that we excited close to the guy of 8 were actually able to change the 8 from A to B. Whereas if we tried all the way at the end of the chain, basically didn't affect our sensor.
But where do the losses occur when you start a magnetic wave? What's happening?
Yeah, that's a very good question. So I keep on talking about these iron atoms, but these iron atoms are not floating in air. These iron atoms are on top of a surface, and the surface is a single monolayer, so a single atomic layer of copper nitride, and that all is on top of a large copper-gold substrate. And this copper nitride layer is meant to decouple our iron atoms from the metallic substrate, because copper gold is metal. but it's not a perfect isolator. On the one hand, we don't want a perfect isolator because if it's not a perfect isolator, then our measuring tool that we use, a so-called scanning tunneling microscope, is actually not able to work at all. So we don't want our iron atoms to be fully isolated, but we do want them to be isolated enough that the electrons that are just floating around and going back and forth in our metallic substrates don't decay our wave. So what happens is you've got this wave. In general, if these iron atoms are just isolated in free space, the wave would go on infinitely long. It would bounce back and forth until infinity. But because it's on this metal substrate, electrons from the metal substrate see these iron atoms, and they hop on the iron atom and they bounce back. And as they do, they catch a little bit of the energy of the magnetic wave. And so this energy of the magnetic wave gets lost to the so-called bath of electrons of the metal underneath.
So in nature, I mean, how strong are magnetic waves in material? Do they kind of pop in and out of existence, all across a monolithic piece of iron? Again, what's the consequence of them happening or not happening? What does it look like, again, if you have a magnetized piece of iron? What's happening?
Yeah, so in a magnetized piece of iron, what's happening there is you've got billions, trillions, even more atoms all having their magnetic moment pointing in the same direction. Even there, it's possible to have magnetic waves on top of this coherent state, which would cause a little bit of noise in the magnetic properties. But I would say in general, it's a very small effect in these bulk materials, which is why we downsize to the point that we're not in bulk material yet. And then these magnetic waves are not a small effect anymore. But yeah, the energy of these magnetic waves is in the order of milli-electron volts, which is very, very, very small. So that means if I've got a bulk iron at room temperature, just the fact that the iron atoms are wiggling around so much and the electrons in the atoms are wiggling around so much due to the temperature, that already destroys any kind of magnetic waves. They will still exist, they will still happen randomly, but they will decay so fast that you won't really notice it. So in our experiments, what we did is we did everything at 1 Kelvin, so quite cold.
So is this more that you were able to build a sensor that's incredibly tiny, or is it the fact that you're able to measure magnetic waves of more importance, or both?
Yeah, so for me personally, what's more important is that we're able to measure these magnetic waves, because what happens initially before we were able to build this detector is we were able to induce magnetic waves, but we can only measure them at the same location as where we induce them. But if we want to know whether these magnetic waves travel, in a chain we have shown that they do travel, but if we want to build more complicated structures and see how they travel in them, we want to have some kind of sensor to tell us how these magnetic waves propagate in these different structures. Since our current measuring tool is not able to do that, we needed to build something new. Now, the fact that it's 11 atoms large, to us, whether it was 11 or 15 didn't really matter. 11 was just the number that it happened to be. The fact that it's so small is a necessity in some sense, because all of the things that we are investigating in our lab are always going to be in the atomic scale. So it's always going to be, between 1 and let's say 20 atoms. So then if you've got a very large sensor, that's going to be an issue as well. So you want your sensor to be approximately the same size as whatever you're going to measure.
Are there any quantum effects because the sensor is so small?
Yeah, definitely. So the fact, so I mentioned that this guy of 8 can switch from state A to state B, right?
Yeah, is there such a thing as magnetic state tunneling?
Exactly.
Or is it in multiple states at once?
Exactly. So we're actually making use of that fact. So normally, this guy of 8 would actually need to get a lot of energy in the order of, let's say, 10 milli-electron volts, which is something that we don't provide it, and something that the temperature also cannot provide to it. Yet it's somehow able to go from state A to state B. And that is exactly using quantum mechanics. So there's a small overlap, as we call it, between certain states. And using that and the fact that there's a small energy difference allows for this switching from state A to state B. If it wasn't for quantum mechanics, it would just be stuck in state A forever.
Oh, okay. I thought you were encouraging the switching.
Yes, we are encouraging. Okay. We are encouraging a switch by changing the energy spectrum, but we're not changing it so much that using classical mechanics, it will be able to go from state A to state B. So.
Oh, okay. So you're relying on quantum mechanics that a small percentage of the time there'll be this essentially tunneling effect that causes a change in state or propagation.
Yes, exactly. So the so-called energy barrier between state A and state B is in the order of 10 millielectron volts. But what we're doing is we're making a small difference between these two states in the order of 100 micro electron volts, so 100 times smaller. But even that small difference is going to be enough for it to want to go from state A to state B using this quantum mechanical effect of state tunneling.
But also the temperature, the low temperature is probably important, so that the wavelength essentially of all the atoms involved is big enough that it's overlapping and you have a coherent state, right?
Yeah. So we would not be able to do this at temperatures above 10 Kelvin. We have done the measurements at 1 and 4 Kelvin, but if we start going higher, then we run into troubles with so-called thermal smearing.
So, I mean, most materials aren't hanging out at 1 Kelvin. So how is this going to translate to materials at room temperature or even materials that are, at any operating temperature, commercially? What do you think is going to be the effect, or is there a long road ahead of you in terms of understanding these?
So, I mean, that kind of comes down to the question, what is the purpose of science? On the one hand, is it to understand the world? Is it to develop technology? I would say it's a combination of both. You can only develop technology once you understand the world better. In terms of whether our specific sensor is going to end up in your phone at some point, I very highly doubt it. Instead, I would expect that this sensor can be used for us to understand better how these waves propagate. The goal of this was not so much to develop technology that's going to be commercialized. Rather, it was used to help the scientific community have extra tools in order for the scientific community to advance.
So you don't get in room temperature materials, regardless of what they are, what the effects are. But it's probably safe to say that, in order to understand quantum effects and materials in certain states, in phase transition or at very low temperatures or, in any state of it all, you want to characterize the quantum effects. And one of those effects is this magnetic, conduction or induction, whatever you want to call it, or propagation, magnetic wave propagation. Yeah. Is that a fair assessment? Or?
Yeah. In general, what science tries to do is just simplify everything until you can make all the numbers 0 except for 1. So try to make temperature 0, try to make the number of atoms 0 except for 1 then. Just try to simplify everything and then start from the bottom up. Like that.
What do you think is happening in an integrated circuit? Now the gates are getting to be just, a couple atoms thick. So how do you think this magnetic wave propagation is affecting circuits? Maybe that's the first use case, and better understanding their properties and behaviors.
Yeah. So most integrated circuits right now are using still electric waves, so wave or electrons moving around. That has a disadvantage of also having heating, because your electrons are moving and there's a little bit of friction, which causes heating. The advantage of these magnetic waves is that there's no mass moving, and so there would be no heating. Those are kind of still two different realms, but it is true that as you make everything smaller, you're going to end up in situations where you're going to have these spin waves, regardless of whether you want them. But you can still make these transistors using materials that do not show any magnetic properties, and then you can kind of overcome them.
Okay. So I guess there's a long characterization ahead to see what their significance is, but at least you're getting there. This sensor, making it itself, how did you get these 11 atoms isolated and then arranged properly? And how fine tuned are they? Like, are they truly in a line? If they're off by a half an atom thick, how straight is this line? Like, how good is it?
Yeah, so half an atom off would be very off for us. So all of what we're doing is done in a so-called scanning tunneling microscope. So a scanning tunneling microscope is essentially a super sharp needle, atomically sharp, that we bring really close to our surface, but not to the point that it touches. There's about one atom in between. At this point, we have a different, or a kind of similar tunneling effect, where electrons tunnel from your super sharp needle to your surface, to your sample, to your substrate. This causes an electric current, so flow of electrons. And since this flow of electrons, this current, is exponentially dependent on the height, basically we can have our super sharp needle or tip to provide a kind of height map of our substrate. So we can make the images with that. So that's always nice. But we can also use this tip, this needle, to literally pick up a single atom and place it somewhere else. And since we are using a substrate that has a square lattice, we can basically end up putting our atoms on points anywhere on this square lattice. So it's very easy to make straight lines like that.
Okay. And again, how straight is straight? Like, what's your tolerance, you think? And if you're off by literally one atom's width, can you tell? And I would think that would make a huge change in your sensor, whether it works or not.
Oh, yes. So what we do is our guy of 8, for example, there's 2 lattice sites in between the atoms. And between this guy of 8 and the guy of 3, or the input chain, there's 3 lattice sites in between. So we're talking about a difference of 100 picometers, or maybe 200 picometers. And that is enough to significantly alter how they couple with each other. The good thing, however, is that the atoms like to stay in these lattice sites. And with our tip, we have precision up to tens, perhaps even a single picometer. So it's not that difficult for us to pick it up and drop it exactly at a lattice site. And even if we drop it slightly off center, it will fall into the center. So that makes it quite easy for us to align these things.
Yeah, I wonder, could you use this as a ruler to judge the linearity or flatness of a surface?
Yes, definitely. We are able to see atomic steps. So if you've got a surface that you think is atomically flat, give it to us and we can tell you how atomically flat it really is.
Yeah, I guess this will have a lot of uses, in addition to the magnetic waves. So very interesting.
Yes.
How long could you make this? You think where it would just it literally would act as a ruler? If you made it, 100 atoms long, do you think that would be very useful?
I don't know if it's going to be useful as a ruler. At that point, you might as well just use your needle, move it across a certain distance, and using your...
Well, no. Here's why I say it. Like, when you're doing... like, when I see, like, electron micrographs, scanning electron, SEM, TEM, whatever.
Mm-hmm.
What if you had also on the slide this... Again, I'm just going to call it a ruler, or a certain number of atoms length. Could you literally use, some kind of machine vision to get you much more accurate sizes and dimensions of things when you're doing this?
Yes. So there are sometimes collaborations with our group and different groups where they want something scanned using our scanning tunneling microscope, and we can tell them how the surface looks like on atomic into atomic details.
Okay. Well, I guess there's like I said, a lot of uses, which is great.
Yeah. So the scanning tunneling microscope was invented in 1973, and it got the Nobel Prize. I don't think it got it that year, but shortly afterwards.
Yeah. Do they have any trouble resolving the size of things in in these kind of microscopes, or like would your sensor work or help, or there's really no need for it?
So I would say the only limitations for this microscope to work is that whatever you're going to measure needs to conduct electricity. So you cannot really measure anything that's non-conductive, but anything else you can measure up to atomic precision.
Okay. Okay, well, very good. Well, excellent. What's the best way for people to keep tabs on, the progress of your work in the sensor? Where can they go?
So, on one hand, there is our group website, which is OTTELAB, which is OTTELAB.TU Delft.nl, which is from my group. But I also have a YouTube video which further explains how the system works. I am trying to see if I can find the YouTube link, and I can hopefully say it out loud.
Yeah, go ahead. Yeah, definitely.
Yes. So let me go to the YouTube page. So the video would be youtube.com/ISD capital D, capital E, LXU, capital N, 64. Alternatively, you can just look up on YouTube, type for 11 atom sensor, and that should give you the video as well.
Okay, yeah, that's a simple way to do it.
Yes.
Well, great. Well, Robbie, thanks for coming on the podcast. I know it's late for you, overseas, and I appreciate you being here.
Yeah, no, I appreciate you reaching out to us.
Yeah.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.